All right, so I trust you can see my screen now. All right, okay. So Clarice gave me this title, which is fine. So I went with it. So it's called Theory in Quantum Computing. Because I aim this at the freshman level, I don't have too advanced things. And I would like to try to give you a little bit of a feel of the ways in which quantum computing is different from classical computing. But first, let me just give you a little bit of a motivation. I'm sure you heard a lot of lectures. I've seen some. So a big driver of the field of quantum information science and engineering is quantum technologies. The fact that by using quantum mechanics, we can hopefully create technologies that we cannot with classical, based on classical physics. So the most famous one, arguably, is quantum computing. I will talk quite a bit about that. There's also quantum communications using the principles of quantum mechanics to transmit information in a secure way. Quantum sensing, which I believe you've heard quite a bit about. And then quantum simulation, which is the idea of using quantum systems to simulate other quantum systems. I'll talk a little bit about this. So depending on how, and I should say that quantum biology, which I know is a focus at UCLA, I would consider that kind of maybe a broader category, and then quantum sensing is very related to that. You could also think about quantum simulations being part of quantum computing, but quantum simulation has become a really large field, so I think it warrants its own, kind of its own category. All right, so you've heard a few different talks, but just to kind of summarize everything together, quantum technologies are based on qubits. These are two-level quantum mechanical systems. They can have many different realizations. They can be the two states of a spin. They can be two energy levels out of an atom or an ion. They can be the polarization states of a photon, and even two different levels of a superconducting circuit. One thing that distinguishes quantum bits from regular bits is the fact that you can put quantum bits in a superposition. You've heard also quite a bit about that. And then there's another concept called quantum entanglement, the fact that you can have correlations different from what we have in the classical world. And this can persist even if the systems are spatially separated. And a lot of the quantum communication ideas and quantum networks rely on that. Another very important distinguishing feature of quantum mechanics compared to classical mechanics is that measurement irreversibly changes the state, the quantum state, and does so probabilistically as well. And this is a very, very important and distinguishing feature. I put in a box because we talk a lot about superposition and entanglement, and I think sometimes, especially in kind of broader lectures, we don't talk as much about measurement, but it's equally important. And it can be a good thing. Quantum measurement can be good because it's a critical part of what makes quantum information, transmitting quantum information in a secure way possible. But it can also be kind of a challenge when we think about designing algorithms. And then another feature of quantum systems is no cloning theorem, the fact that you cannot copy unknown quantum states. And that also has important implications for security and the fact that we can do all these secure quantum cryptographic protocols. All right, so there's a lot of qubits. This is not an exhaustive list. Some of these you've heard about under this seminars of this course. These are kind of the ones that are probably the most popular and ones that I have mostly worked on. And I've not worked explicitly on trapped ions, but pretty much everything else my research has touched upon. So there's different types of spin qubits. Spin qubit is kind of an umbrella term, and it applies to several different systems. So one system is the MV center in diamond and similar defects or color centers. I know you had a nice lecture from Clarice on this and probably from a few other speakers. These are atomic-like point defects. They live in inside a crystal. in this case, diamond. There are other spin qubits, such as quantum dots, which are created by depositing gates, these metallic leads over here on a material. There's a semiconductor material forming the interface of two semiconductor materials, forming a two-dimensional quantum gas of electrons. And then these leads create potentials where the electrons can be trapped. These are much larger. The defects are at the atomic scale. These are on the order of 50 to 100 nanometers big. And so are these. These are similar systems, but they're grown spontaneously when you deposit one type of semiconductor on another. And these, on top of having the spin, they also have optical interface. Then there's superconducting qubits, which I know you've heard about, and there's also trapped ions, and also neutral atoms, which share some similar properties, especially in their energy levels. And then there's photons. So the different qubits are good for different things. And in this table, you can kind of see that some are explored more for quantum computing, others are more for quantum networks, and others for sensing. And the reason you have kind of this distinction between the applications is for quantum computing, one of the most important things is scalability. So you want systems that you can grow in a way that you can combine many of them, fabricate many of them in a way that they can communicate with each other and their positions are controlled. And then the ones that are here marked for sensing and networks are the ones that have an optical interface. So that's very important, especially for quantum networks, because you want to transfer information from one point to another. And of course, the way to do this, or at least the standard way of doing this, is with light. All right, so in this seminar, I'm not going to talk too much about specific physical systems. I'll come back to some of those at the end. What I do want to talk about is a little bit at the more kind of abstract level, compare classical and quantum computing. And for that, I will use a pictorial representation of qubits and quantum circuits. And I'll also show you a quantum algorithm disguised as a puzzle. And then, time permitting, I'll talk about a little bit about my own professional trajectory and a little bit about my research. And I also want to say that if you have any question, please interrupt me. I much prefer that than just hearing myself talk in a monologue. So I hope people will feel comfortable to interrupt and participate. All right, so of course, to do any computation, we need some physical system to represent a 0 and a 1. Everything in quantum computing, or at least the vast majority of the theory in quantum computing and in classical computing is formulated in terms of bits or qubits. And that means some physical system that can take two discrete states. So in the case of a classical system, let's just think about a capacitor. And you can think about a capacitor as being uncharged, and you can think of it as being charged. So you can assign state 0 to the uncharged state and 1 in the charged state. And then inside the computer, there's different bits that represent different positions in this binary string, which makes up numbers based on which we can do arithmetic and other operations. So for example, imagine here I have 5 capacitors, and it's well defined which one is the first or the 0th, the first, the second, etc. So then depending on the state of each one, here I have an uncharged, charged, uncharged, charged, etc. I can assign a 1, 0, 1, 0, 1, because I read off, based on this correspondence. And that number is in decimal, it's the number 21, represented this way. So after we assign these, we can also do operations on them by doing gates, we do some physical operation that modifies the value 0 or 1 and the collective value of the whole system. And here I should also mention that the index of this capacitor, in this case, tells us which power of 2 this capacitor represents, okay, in this binary string. Okay, so in everything I'll talk about in the remainder of this lecture, I'm going to switch from this kind of explicitly physical representation on the left, which, you know, we have made a choice to talk about capacitors over here. And I want to switch to something more abstract. And I'm just going to use shapes. And I'm going to allow these shapes to have two different colors, black or white. So there's going to be a one-to-one correspondence. If this is black, then it represents, let's say, the charge state or the bit 1 being in state 1. And if it's white, it represents that bit being in state 0. And the reason that I have different shapes over here is because I consider these different capacitors distinct. So I can say this is the 0th, the 1st, the 2nd, the 3rd, etc. Okay, so now that we have defined that, we can start doing gates. And one thing we can do, the simplest thing presumably, is define a gate that's called add. So what this does is it takes two different bits and it just adds them up. So for example, in the left over here, I have bit 0, the left bit and the right bit both being in state 0. If I add 0 to 0, I get 0. And that's what this number represents over here. If they're both, sorry, if one is 0 and the other one is 1, then I should get the output 1. And you see that these two middle ones give me the bit value 1, because I have 1 in the position of 1s and 0 in the position of 2. But here, if I add 1 and 1, I get 2. And this is kind of consistent. And then, of course, you need to have some way to decompose this arbitrary operation you want to do on your bits into some more elementary operations. So we call these elementary gates. And you can see here one example how you can decompose this. So there's gates that you might have seen in a logic course or a circuit course, exclusive OR and copy. Now, one thing you could ask yourself is this operation here reversible or irreversible? And I don't know if people are there, but it might be interesting to think about this question and see what people think. Is the add operation reversible or irreversible? Okay, right. So the chat says irreversible, and that's right. And the way you see that is there's these two middle outputs are the same. They don't, it doesn't matter where you started from, you get the same thing. So the reason this is something to mention is that in quantum, all the gates are reversible. So we can't just readily use some of these things. We have to first think about how to make the gates irreversible. To make them reversible. So there exists a model of classical computing that's entirely reversible. And in kind of elements of circuit design in quantum computing, we borrow from that. But the point is that you can make any gate reversible by adding additional qubits or bits. So here are some reversible gates. Now I'm not going to think too much about what is actually used in classical computers, which are based on irreversible gates. I'm going to only use gates that will end up also being usable and important in quantum computing. So the simplest thing you can do to a qubit or a bit is to change its value, right? So if it's 0, you can pass it through some box. Of course, what I show here is a box is some actual physical operation. In the case of a capacitor, change the charge. And here white would become black, or 0 would become 1 and 1 would become 0. So this, what I show here, you can think of as the truth table of this NOT gate. And it's all pictorial. We'll continue with this pictorial way of thinking about it, but it's completely rigorous. And if I tell you what happens, to the different input bits, then you can predict stacking circuits together, as I'm going to show you in a minute. So here I can stack two NOT gates, one on top of each other. And the first one flips the color, the second one flips it back. So two NOT gates together, we can say that they act as an identity gate. So they don't do anything. And of course, you can also, it doesn't matter what shape I put here because these are gates that you can act on any bit or any qubit. Okay, then the next thing we need, so there's, I think, yeah, so there's elementary gates based on which you can break up larger gates. I'm not going to talk about things like AND and XOR because those are irreversible, but the gates I'll show you, you can break up any larger gate in terms of those, at least approximately. But in what I'll show you, you can do it exactly. So another gate that is actually reversible is the swap gate. And the swap gate does what it sounds like. It just swaps the value of the two bits. So you see white, white and black, black don't change because they're the same color. But white, black goes to black, white, black, white goes to white, black. And you see that this is reversible. I have 4 distinct outputs. So this is a 2-bit gate, right? I cannot break it up into separate 1-bit gates. I need both bits as the input. And now that I know what this gate does for all possible inputs, I know this gate exactly, right? I know exactly what it would do in any occasion. Another gate that's extremely important in quantum computing is called controlled NOT. But as you can see from the slide, I can actually define controlled NOT in a classical context because I don't have yet any superpositions. And controlled NOT does not create superposition out of classical inputs. When I say classical inputs, I mean a well-defined color, either white or black. C0 is another reversible gate, and it's a genuine 2-qubit gate or 2-bit gate. And as you'll see in a minute, it's also a gate that can create entanglement. So it's a very, very important gate in quantum computing. And when we think about how do we actually realize quantum computers, it's one of the first things you have to worry about on your physical systems. How do you do this gate? So the control NOT does what it sounds like. It's doing a NOT operation on one of the qubits or one of the bits in this case, since we haven't gotten to qubits yet, conditional on the state of the other bit. So here, the target is the one that's under this this plus sign. And the control is the one that's over and under the dot. So what this means is that if you see white in the control, the target will not change. So as you see in the first and the third case, but if the control is black or 1, then it activates this NOT gate and the target bit changes. Let me know if there's any questions so far. And you can think of this also, I arbitrarily chose the second bit to be the control and the first the target, but you could have switched, you can also define a NOT gate, control NOT gate, where you change which one is the control and which one's the target. All right, so let's now kind of try to put that all this into action. So now that we have defined these gates, we can stack them and create circuits. These are still classical circuits. I'm not talking about superpositions quite yet. But we can actually calculating quotes because it's all pictorial, but basically that's what we're doing. What happens to the bits that enter the circuit? And the way you should think of this is you first pass them through the first layer. You change these bits according to this definition, and then you pass this output through the second layer. So if anybody wants to guess, I can pause for a moment to guess what would come out after the first layer. So you could just type, www would be all whites, for example, etc. If anybody wants to attempt. Okay, great. Black, white, white, black. So let's see why that works. So the swap gate just changes white, black to black, white, right? The second one is a control NOT. So all the way to the right, we have the control bit, it's black, the NOT gate will be activated. So the triangle will turn white, and we get that. Now we're passing this through the second layer. What's gonna happen in the first case, the very first, the circle bit undergoes a NOT operation, so it'll turn white. Now the middle C0 is not activated because the control is white. So it's as if that C0 is not even there. And the very last one will turn white because it undergoes a NOT gate. So we get all white. All right, so this is a classical circuit. Now let's start thinking about the quantum case, in which case we don't just have zeros and ones, we also have superpositions of zeros and ones. So as an example, you can think about the position of an electron, or you can think about an energy level inside an atom. And the system can be not only in either of these energy levels, or not only either in these positions, but it can also take these two positions in kind of in a parallel way in a superposition. And I'm not going to use this mathematical formalism shown over here, but I just put it here for reference because you might have seen it in other lectures. Instead, what we're going to do, instead of using, this notation that's called Dirac notation, we're going to just introduce something that's a little bit more intuitive and pictorial. So what we're going to do is we're going to use this mist, this kind of little cloud with a separation over here. And what this is by definition, it's a superposition of 0 and 1. So it's sort of, sometimes, people say it's black and white at the same time. That's of course a little bit of an abuse of language, but we can kind of think of that in a rough way. So now what we're going to, and I should also say that this is the formalism I'll be using that has this notation for superposition is borrowed and adopted from the very nice book by Terry Rudolph, Qubits for Quantum, which I strongly recommend. It does not assume any advanced math or any background, but it's completely rigorous. All right, so now that we'll use this for superposition, we need to start thinking about what happens to superpositions, both when we make measurements and also when we do gates. So as I mentioned in the earlier slide, measurement is really different and bizarre in quantum mechanics. It's something very different than what we're used to in our everyday life. And what happens is if I have a superposition shown here, white, black, equal superposition of white, black, meaning I have the same number of white as I have black states in here. If I make a measurement and I use this symbol that's taken from the IBM quantum experience interface, then with some probability, I will get, with 50% probability in this case, I'll get a white output, and with 50% probability, I'll get a black output. So if I just run this experiment once, then of course I have no way of knowing and predicting beforehand which one I'll get. All I can say it's 50-50. If you have a whole bunch of these and you run, a whole bunch of these states, different copies of these states, and you run the experiment over and over, then on average, you'll see 50-50. Of course, you'll have to take the infinite limit to be exactly 50-50, but on average, you'll see half black, half white. And one thing to note is that the randomness people talk about in quantum mechanics comes entirely from measurement. If you don't make measurements, everything evolves entirely deterministically, but then as soon as you make a measurement, probability comes in. So since we have to deal with probabilities here, we also have to know what's the rule. And the rule actually is not that here, in this example, I still have one qubit, and it's in a superposition of black and white, but you see here it's an unequal superposition. Here you could be tempted to say, oh, black is 3 times more likely than white because I see 3 black, 1 white, but actually it's not the ratio of how many you see here, it's the ratio of the square. So you'd first have to square and then divide to see what's the relative probability. So if I square 3, I get 9. If I square 1, I get 1. So that means that black here is 90% probability and white 10%. This is a nice example because it happens to be normalized in the sense that 90 plus 10 equals 100. That's not generically true. So we have to do something called normalization that I'm not going to worry about too much in this lecture. But if I had some other number here, if I had 4, then I would have to square that, and I would square the 1, and those would not add up to 10 or to 100. Okay, so how do we create superpositions, right? That's the very important question, because if I can have superpositions, as I'll show you in a minute, you can do really non-trivial things. And we are going to define a gate that's called Hadamard. H stands for Hadamard. And what this gate does, is a single qubit gate. And if I put a white, a 0 over here, I get a superposition, equal superposition of white and black. If I put black or a 1, I again get an equal superposition, but now there's this minus sign. So this state has the same probability of black and white as this, because if you remember, I have to square to get the probability. But it's a different state, and the difference is this minus sign. Any questions so far? Okay, you can also type any questions in the chat. Okay. Now, what this Hadamard gate does, it creates the superpositions. And I told you that if I make a measurement afterwards, I'm going to get 50% white, 50% black. So this is how, the full circuit will look like. I explicitly put here the measurement box because, as I said, measurement acts very differently in quantum. So we have to kind of, keep track of the fact that we have a measurement over there. So I input here a whole bunch of different white. Maybe I should have made the colors, the shapes different, but then I would have to make a whole bunch of different shapes here. So the way you should think about this is that I repeat the experiment with a qubit every time, 1 qubit at a time. And then I make a measurement and I get 50-50, right? So one question you could ask is, how do I know superposition exists and I don't just have some classical probability distribution? And what I mean by that is the following, right? You could ask yourself, is the Hadamard gate equivalent to what's shown over here? So what's shown over here is some little demon inside the box who's holding a NOT gate and who's also holding coin, a fair coin. So you could, think of this. The question is, can we think of the Hadamard gate as when a qubit comes in, this little demon here flips a coin, and if it's heads, just throws the qubit by, so to speak, without changing it. And if it's tails, it applies the NOT gate first, so white becomes black, black becomes white. Right. So the question is that what happens with the Hadamard? And you could ask, how would you test this, right? So if I had here someone flipping a coin inside each of these boxes, what would the circuit give me? So if I were to add a measurement at the end of the circuit, maybe I should have done that as well. What would I have gotten if there was really a coin flipping person or demon inside each box? I'll wait if people want to type in the chat. Good. It'd be 50-50, right? Because the first box would just randomly change white to white or black, leave it white, or 50% make it black. So then the input in the next box would be either white or black randomly and with equal probability. So then this would also change it probabilistically or not, and then I would get something random. However, if you do this experiment, what you actually get is you get 100% white on the left and 100% black on the right. So this means that I cannot think of the Hadamard gate as someone randomly changing, with 50% probability the color. of the qubit, it's doing something much more kind of intricate and profound on that. It is actually creating the superposition. And you can think about the word coherent we sometimes use as exactly that. It's not just some classical probability distribution that's going on. There's something much more subtle that is described with the superposition. So when I actually put two Hadamards, their effect cancels, and it's as if I have the identity. So then this picture is actually wrong. I cannot think of the action of a Hadamard as some classical process described by a probability distribution. Something that's really strange and different about quantum mechanics is that if I slightly modify the experiment and I add a measurement after each Hadamard, so here the only difference is I've added one more measurement after my first Hadamard. This measurement now enters, makes this probabilistic and makes the superposition that was created from the first Hadamard. It forces this qubit to choose, is it black or is it white? So that means that I get now some randomness at this step. And then when I put it back in here, now it's equivalent to that random coin flipping situation. So just by adding this extra measurement, I've entirely changed what I get in my experiment. Yeah, that's a very good question. So one question was, where's the -1? What is it? Where is it showing over here? So I've not explicitly shown it yet, and I'll show it to you. But let's go here, and it's a very good question. Students often ask this question: what does this minus sign mean, or what does it do? One thing that I mentioned before, so I'm going to try to motivate it and maybe not explain it fully satisfactory way. But one way to think about it is that imagine this minus sign was not here. Then this would be entirely the same as this. And then this gate would not be reversible. So I need something that distinguishes this superposition from this superposition. In fact, the way you can think about it is that the white and the black are as different as it gets, right? The white is the negation of black and vice versa. When I pass qubits through gates, through quantum gates, I have to preserve this property that these are really different. In a vector language, we call them orthogonal. That means that if it's this on the left, then it's definitely not that. There's no overlap between the white and the black. And that minus sign achieves that. It actually, this state and this state are completely orthogonal. It means they're as different as possible. And the minus sign play is important in calculating what happens over here on the right. And I think I have that in a slide, in a few slides. All right, so the way you can think about superposition is that it's there. If we don't have it, then we cannot explain experiments. So it's kind of weird because it's like, it's like as if this skier has taken these two paths at the same time. But then if someone peaks, right, if you have a measurement, then you're forcing them to take a path. So by just looking or measuring, you're destroying the superposition. Okay, so this is not very well animated. Let me fix that. Okay, here. So because this pictorial formalism is pictorial, it's not exactly math, it's representing math. It's actually representing linear algebra. We need to postulate some rules about it. And these rules would come out naturally if we were just dealing with vectors and linear algebra, but I don't want to assume that. So what we need to do is we need to just postulate some rules that hold about these mists so that we can actually do calculations. One thing is that the order doesn't matter in here. So white, white, if I have two qubits, white, 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 black, superposition is the same as white, black, white, white. Another interesting thing is that if I have two entries with opposite signs, as the black one does here, you can actually subtract them. So the black goes away over here, and I just get white. And if I just have one thing inside a mist, that's a classical state. It has a well-defined color, so I can get rid of the mist because there's no, there's no superposition really. If I have the same ratio of white, if I have white and black, I can divide, for example, here I have the same number. So it's the ratio that matters. So here I can get rid of, one white, one black, because I still have 1 to 1. I can also get rid of mists inside other mists, but I have to be careful to preserve correctly the number of qubits. I can show you an example where you have to be careful. But in this example over here, I go back to the top. So this is just white, black. Here, because the 1 qubit is white in all the entries, I can pull it outside. So this is very analogous to doing algebra and pulling out a common factor. So this 2 qubit state is actually the same as the first qubit being in a well-defined classical state white, and the other qubit being in a superposition. And then finally, I can also sort of multiply together different mists and this FOIL method. And I can get this, one big mist, which is kind of the opposite of factoring things out, shown over here. All right, so this is just a set of rules, and you have to refer to them when you do calculations using this formalism. But the nice thing about it is that, you can refer to the set of rules and you don't need to have learned linear algebra to follow what's going on. All right, so the next thing we need to discuss is how do I mathematically, pass the superposition through a box. The way you do it is you just pass every element of the superposition independently, and you preserve the mist. So this is what is called linearity in quantum mechanics. And then this is what I get, right? So now I'm just going to start applying the rules I showed you in the previous page. The first rule is that I can remove inner mists from the outside mist. So I get this. And now you see that I have black, both occurring with a minus sign and without a minus sign. That means I can subtract them. If I do that, then I just get white. But if I have 2 copies of white, that just means white. So I can reduce that, and then I can remove the mist and I get white. So this shows me, that if I put 1 Hadamard and I have a white input, I get the superposition. The second Hadamard takes the superposition and outputs white. And then I can also do the same with the other superposition, the one with a minus sign. And now you see the difference, right? Now I have this overall minus sign on this mist. So that means that the minus sign goes in front of the white if I distribute this minus sign. I just distribute it multiplicative. So then the white ones cancel and I get black, black. And then I have just 1 black, which is a classical state, and I end up with black. And then I have consistency in the diagram I showed you with 2 stacked Hadamards being the same as an identity. I'll pause here for a moment in case there's any questions.
Hi, Professor, I have a question. So a few slides ago where you show that inserting a measurement between the 2 Hadamards that basically destroy the magic. Is there any way to, for instance, if the qubit is some kind of double quantum dots and then we have some auxiliary charge sensing dot next to it, is there a way to perform the readout, but then also let the original qubit to propagate through another Hadamard and then still get the magic, or is even the slightest charge sensing action will destroy the magic? Yeah,
that's a very good question. So in general, if you measure, there's always a conservation of, you cannot extract information for free, so to speak, right? If you extract information, you're affecting the state. Oh. There's something called weak measurements where you can extract less information and then you disturb the state less. I'm not going to talk about those here, but you cannot ever know everything there is to know about the system and still, preserve the superposition.
Okay.
You can ask, if you have a state in a superposition and you want to know which of the 2 superpositions it is it the white black or the white minus black? There is a way to do that and know exactly, because you can pass that through a Hadamard, then it becomes a classical state like I showed here, and then you can measure. Right, but at the end you always, destroy the superposition when you make the measurement.
Okay, thank you.
Great, thanks for the question. So now let's see what happens if I pass 2 qubits through a 2 qubit gate. So what I can do is I can start with a superposition of 2 qubits. And now if you remember, I'm gonna just quickly flip back to the slide with the rules. Let's look at this rule over here, where I have white circle in both entries. That means I can pull out the white circle. So this qubit is always in state 0. And that's actually the state I input in the gate I'm showing you now. So I'm gonna flip back there in the C0 case here. So you see the circle, I can factor it out. And then I follow exactly the same rule. Now I pass this entry through, and it becomes this entry. So I follow the C0 rule. C0 does not change anything if the control is white. So I end up with white, white. But now in the second entry, the control is black. And that means that the circle is now flipped to black. So this input becomes this input. So I get white, white, black, black. This input, this output state is really different than the input in a qualitative way. So you see, as I mentioned at the beginning, this is what we call a separable state. It means I can separate out the 2 qubits, and they each has its own quantum state. It's fine if it's in a superposition, but I can assign a particular state to each one, right? The circle is always white in the state, and the other qubit is in a superposition, white and black. However, this final state over here, the output I get is white, white, black, black. There's no way to assign a particular state, not even a superposition state, to one of the qubits. These 2 qubits now are kind of they're inseparable. I cannot say that one of them has this state and the other one has that state. Their states are completely correlated. And in fact, if I make measurements on one, then I am destroying the superposition and I am determining the state of the other one. And you can even imagine taking the 1 qubit in one location and the other qubit in a different location. And if you do that carefully enough, what I mean, meaning you don't interact with the environment, we're not going to assume any such issues, we're going to assume the idealized case, then you can have these correlations persist arbitrarily long distances. And this is a simple example of what we call an entangled state. Actually, this is one of the 4 Bell states, which is very, very important in quantum information theory and in quantum teleportation. Are there any questions on this? So this is one of the most remarkable properties of quantum mechanics and quantum information, the fact that such states exist. And this is, you know, a feature that troubled the people working on quantum mechanics when, you know, the theory was first established, because this is really against all classical intuition we have. Okay, if there's no question, I'm just wrote here what I just said. And I want to show you quickly, I know we're kind of running out of time, but I want to show you quickly one example of something you can do with all this stuff to get a feel of, you know, why is quantum computing more powerful in certain tasks than classical computing. And I'll show you a puzzle that my colleague at Barnes came up with called Money or Tiger. And this is phrased as a puzzle, but it's really a quantum algorithm that's in most textbooks. So here's the premise of this puzzle or this game. You can think of this as being a game that you're trying to kind of beat. And this is what happens. So you have 2 doors. Each door has a color associated with it. So at the left here is white, the right is black. And these are and there's money for sure behind one of the doors. There might even be money behind both doors, which would be great. But there also might be a tiger behind one of the doors. And the reason that's problematic is that you can only open both doors with this button, right? Let's say these are locked and this is the magic button that opens both doors at once. And then there's this slight help over here, this tiger box, which lets you query each door. So you can input a white qubit and a test qubit. And if the test qubit changes color, I'll show you in a minute, then it means that particular door you're testing has a tiger. If not, then there's no tiger. However, you can only use this tiger box once. And that's why this puzzle is set up to be kind of evil, at least classically, because you could test the door, but if you're unlucky and you test the door that doesn't have the tiger, then there might still be a tiger in the other one, and the button would make you open both. So here's the 3 different scenarios of what's happening behind the doors. You could have money, tiger, money, money, tiger, money. Of course, ideally you would want to have the middle one, because if you figured out you have one of the left or the right, you wouldn't even open the doors because you cannot just selectively open one door. So what you want is, ideally, you would like to be able to use this tiger box in a way that told you, are you in this middle situation or in one of the left or right? If you're in the left or right, you would not do anything. You just give up on the money. If you're in the middle, you take the money and walk away happily. All right, so here's what this tiger box does, the tiger detector. What I mean by this shaded shape is it can be white or it can be black, right? So you can input a white, you can input a black. If you want to test the white door, you put a white square. If you want to test the black door, you put a black square. And then you have this test qubit. So you pass both these qubits through this tiger box. And if the test qubit does not change color, no tiger, and we're all good. If the color changes, then there's a tiger and you should not open the doors. So here are the 3 possibilities, and this is what the tiger box would look in each case, right? If there's money both behind both doors, then the color of the test qubit never changes because only the tiger makes it change, right? So whatever you put in, you get out. If there's a tiger between the black over here, then only when I have a black square with the color of the circle change. So that's the second and the 4th case. And finally, if there's a tiger behind the white door, then when I have a white square, 1st and 3rd case, then this test qubit would change. All right, so let's say now we don't have access to quantum gates yet, we just have classical. What can we do, right? So if we can only use classical states, how many times would we have to use the tiger box to be sure there's no tiger? Of course, the answer is we have to use it twice, right? 1 for each door. There's no way you can beat that classically. So you can think about it. Let's think about cases, right? Let's say I run the tiger box once with white for the white door. And let's say I get white over here, right? If I get white, I don't know, am I in case 1 or case 2, right? There could still be a tiger behind the black door. So then I would have to run it 1 more time, and then I would get something unambiguous because I would differentiate between the 1st and the 2nd case. So hopefully it's quite obvious that classically there's nothing better I can do, right? I need to use this tiger box twice. So if I were to actually be playing this game, with someone, a TV show host or something, there's no way I would win this. I would not want to be eaten by the tiger, so I would just not play the game. However, if you use quantum circuits and quantum states, then you can determine if there's a tiger with just 1 shot. So I don't have time to go through how the math works, but you can actually work based on the rules I showed you. You can work out every possible case for the tiger box and see that if you input 2 black qubits, so 2 qubits in state 1, I pass them through Hadamards. I create superpositions over here, so I get quantum states. Then I pass them through the tiger box. And then I have another set of Hadamards. Then, if I don't have a tiger, I get black, black. If there is a tiger, I get black, white. So what's interesting about this is that I can do this by only using the tiger box once. And this is something that's very obvious and clear I cannot do classically. The other interesting thing to note is that this circuit does not tell me where the tiger is. What it tells me is that there is a tiger somewhere. So I'm just finding out the information I want and not more. So this is kind of, I think the last slide I have on the more algorithmic side. This is actually, this algorithm is called Deutsch algorithm in the quantum computing literature. And it's here disguised, to be about a game or a puzzle, but in reality, it's about a function that you need to determine if it has certain properties. No, so in this case, I'm actually making a projective measurement at the end. So the measurement here is absolutely projective. And I'm not destroying anything because the output state over here is classical, right? The circuit, you input a classical state, meaning I input a state with no superpositions. I create superpositions as I run the circuit. And then I'm sort of undoing those superpositions. And that information that I want is at the end encoded in the output states, which are classical. So the measurement I would make at the end of the circuit, I didn't put it because I have classical states, so it doesn't matter, nothing's going to be destroyed here because I have classical states, but the measurement here would just give me exactly what you see. It would not destroy it. Any other question? Right, so what I was hoping to highlight with this example is that with quantum states and quantum gates and circuits, we can speed up certain types of calculations. We cannot speed up every single computation because in general measurement destroys states. So we have to somehow cleverly design our algorithms such that the measurement at the end gives us information and does not destroy the information. Okay, and another thing I want to mention is that the notation I used with shapes, you can easily think about mapping them into circuits the way people use in the community. And the way you can do that is you can take your shapes, first rotate them clockwise, and then you can assign a line to each of these qubits and start creating circuits. There's a really nice tool by IBM. What I really like about it is that it's drag and drop, so you don't even need to know any programming language, and you can go and create your own circuits. It's absolutely free and a really nice resource. All right, so if there's a few minutes left, I think we started a little bit late, so maybe I'll take questions here, and if there's no questions, I'll just quickly go over this last part. All right, so the organizers also asked me to say a little bit about my professional trajectory. You might be able to tell that I have an accent. That accent is from Greece, where I grew up, and I also did my undergraduate studies in physics. This is a beautiful picture of the water, the ocean in the north coast of Crete, in the biggest city called Heraklion, where this is actually the view from my parents' house. Then I went to the UC San Diego, very close to where you guys are, and I did a PhD in physics. I started by studying theoretically optical controlled spin qubits, in fact, quantum dots, the ones I showed you in the early picture. Then I went and I did a postdoc, and I held a staff position at a government lab called the Naval Research Lab in Washington, DC. And I moved about 7 years ago to Virginia Tech, where I started as an associate professor, and I'm a professor of physics. So I'm just gonna maybe leave up, I had some more things like example of types of problems I work on, but maybe I'll give you another chance to ask questions. And you can ask me about things I said or anything else, or
Yes, I do have a question. So I heard you mentioning projective measurements. So I guess my question is, in practical quantum algorithms, in order to determine the state, how many times of measurements do you need? And then do you prepare like many qubits in parallel with the same fashion and then measure them? at the same time, or is the algorithm done on the same qubit sequentially, and then you measure it? How does it work?
Yeah, so there exist algorithms such as Shor's algorithm, which is a very famous one for factoring, or for helping you factor integers into their prime numbers, where you actually have to run it over and over and do some statistics. And in that case, it wouldn't matter. You can use spatial or temporal resources. You could run, something in parallel if you have a bunch of quantum computers. I think the way we think about it is that we'd probably have one powerful quantum computer, at least initially, and we would just run that over and over. But conceptually, they're the same thing.
So like practically, how many times do we have to do this kind of measurements?
It depends a lot on the algorithm and on the system.
Okay.
So you would want, you would not want to have to measure an exponential number of times in the size of the system, right? So if repeating the measurement is part of your algorithm, meaning that the output is probabilistic with a high probability, that probability has to be high enough that the number of times you have to measure scales well with the system. But that's very algorithm dependent.
Okay.
And so I'm skipping over some things about my own research to just tell you that we are running a summer school. I'm not sure, I know some of your undergrads. This is aimed at somewhere between high school, advanced high school, and early college level. It's based on the formulas I just showed you. It's also using the IBM systems. It's a 4-day event in the beginning of August. It's all virtual and all free, so anybody can register. And we expand on things I showed you. We do talk about this money or tiger, we work through it, but then we also talk about teleportation, other quantum algorithm, which is Grover's algorithm. We talk about entanglement, and if there's time, even quantum error correction. So feel free, to register if you want. If you want any more information, feel free to also email me. And I should say that we can offer this for free because we have awesome volunteers, most of them, but not all of them, from my group. So I just want to show you, some of the people who will be helping us out with the summer school. They're very fun and very knowledgeable, so it should be a fun event. Yeah, so that's all from me. Thank you.
Thank you so much. Are there any more questions from the audience? I have a question. So is there any way to represent a mixed state with your diagram approach?
That's a very good question. You could have, I have not thought of an elegant way of doing it, right? Because mathematically, density matrices are matrices. So you would think they have to be boxes, but I don't think there's a nice and elegant way to do that. Maybe there is, and I haven't thought of it, but I have thought about it a little bit. You could, though, assign probabilities and kind of do it in parallel. Do each evolution in parallel, and then just add them according to the classical probability distribution. So you can do it, but mathematically, it's not as elegant, I think, as the correspondence of pure states.
Well, I guess you sort of can, you already have a tensor product embedded into this mixed representations. Yeah, so maybe there is some way around here. Okay, thank you. Any more questions? Oh, if not, let's all clap virtually to our speaker. And thank you so much for attending. And thank you, Sophia, for presenting.
Bye, everyone.